Hello, in this video we're going to find the extreme values of f of xy equals x squared plus 2y squared on x squared plus y squared less than or equal to 1. So in this problem, it's similar to what we did in the last example, but what's different here is that our constraint has an inequality in it, and that means we are on a disk. Okay, and in the last problem we were just on a circle, which is that essentially the boundary of the disk. And in the last problem we did find that there was a max value of 2 and a min value of 1, and those were on F, subject to the constraint that we're looking at points that satisfy this circle. In this problem, we'll still look at the boundary, but we're also interested to know where the max and mins of any points interior, in other words, any points on that disk. Now, just from the graph that we've drawn right now, you might be thinking to yourself that the minimum is no longer going to be on the surface. It's probably the case that the minimum is going to be right there at the origin. Okay, and if you plug that point in, the minimum at 0, 0, that is going to be a min value of 0. Our max, just because the function is increasing in the way that it is, that max is still going to be 2. But let's work through the analysis so we can convince ourselves that our intuition is correct. Okay, so I'm going to reuse my results from the last video. So in the last example, we found that the max of f on the circle, right, subject to the constraint, is 2, and that happens at the point 1, 0, it happens at the point 0, 1 and 0, negative 1. And similarly, there's a min of f on the circle, and that is a min value of 1, and that happened at 1, 0, negative 1, 0. So it remains to check the interior. So it remains to check for max min on the interior. And for this, we just need to do our second derivative test. This is like a max-min problem from a previous section in our textbook. Okay, so let's go ahead and do our second derivative test. For the second derivative test, the first thing we need to do, we need to find the critical values of f. And remember, f of x is our function x squared plus 2y squared. So the critical values, let's see, we need the partial derivative of f with respect to x and the partial derivative of f with respect to y. Setting both of those equal to 0 means that we need 2x equal to 0, and we also need 4y equal to 0. In other words, x is 0, y is 0. The only critical value is at 0, 0. Okay, so the next thing we want to do is we want to do the second derivative test. We want to compute d, and we want to compute d at our critical point, which is the 0, 0. And to do that, we will do our second derivative of f with respect to x, evaluated at 0, 0, times the second derivative of f with respect to y, evaluated at 0, minus the mixed partial derivative at 0, 0 squared. Okay, so let's go and compute those results. I know that the derivative of f with respect to x is 2x, and so that means that my second derivative of f with respect to 2x is 2. Similarly, the second derivative with respect to y will be 4. And our mixed partial, if I do the derivative with respect to x and then with respect to y, or the other way around with respect to Clairaut's theorem, that's just 0. So d evaluated at 0, 0 is just going to be the constant function 2 times the constant function 4 minus the mixed partial, so that's 8. In other words, our d value is positive. Also note that the second derivative with respect to x is positive, and when you've got d positive and your second derivative with respect to x positive, this implies that you have a local min, and we have a min at our critical value 0, 0. If we plug that into the function, that actually is the absolute min of the function, which is 0. So to summarize, f has max value 2 on the disk x squared plus y squared less than or equal to 1. And f has a min value 0 on the disk x squared plus y squared less than or equal to 1. So that min value of 0 was the winner in terms of minimum values. Right before we found a min value of 1, but that was on the surface, on the boundary when we plugged in the boundary of that circle. And now we're also looking at all points interior to that circle, so on that disk, and we found an even lower point, so that's our winner for the minimum.